Now let's try and understand the Newton-Raphson method, which is a very, very simple example. Here you get to understand the process. We also try and provide you a graphical insight of what is going on, and also you would get yourself familiarized with the procedure, how exactly to proceed in a typical situation where you are applying the Newton-Raphson method. If you are having a graphical calculator at your disposal, then the method becomes absolutely irrelevant, because the moment you plot the graph of a function, wherever it crosses the x-axis, your roots are got. Now we can apply Newton-Raphson method whether you're talking about a pure polynomial, that is an algebraic expression, or whether you are talking about a trigonometric expression, you are trying to find the roots, or whether you are talking a combination of exponential, algebraic and trigonometric entities. So therefore this is something that can be efficiently applied if your initial guess is close to the root that you expect. Now let's try and understand this particular method systematically. That is where we have chosen a very, very simple problem. We intend to find the square root of 5. You can actually have two values for square root of 5. One is positive value and another is negative value, because when you take square root, it is plus or minus the value, but here we are trying to estimate the positive value. So let's understand the problem in its entirety. Here the function whose root is square root of 5 is not given. So our first task is to develop an expression for the function whose value when becomes 0 gives you square root of 5. So what you are fundamentally estimating in this method, you are finding the root. That means you are trying to find x equal to root 5. You are trying to estimate this, right? So if I simplify this, it becomes x square is equal to 5, and if I further simplify, I'll get x square minus 5. When this goes to 0, you are going to get the value of root 5. That means this is the function which is f of x. So therefore this is what you will have to deal with. That means a parabolic function is given to you, an algebraic function is given to you, whose roots are the roots of 5. Am I clear? So first task is cut out, and that is executed well. That means we have found the equation of the function which when crosses the x-axis will give you the roots of root 5. So if I represent this particular entity geometrically, what I will get? You now recall the shifting of the function that we discussed under Laplace transform. That means if I am talking about a function y is equal to x square minus 5, if I were to subtract this particular value, that is 5, from x, that is if I were to write like this, then the parabola would have shifted either to the right or left, depending on whether I am subtracting or adding 5 from this x, right? But here I am subtracting 5 from x square, rather I am adding 5 to y, because this can also be represented as 5 plus y is equal to x square. In such a case, the function can either shift up or shift down. That should be understood carefully. Now what I am doing, I am adding 5 to y. That means the function is going to shift down. Shift down. This is the parabola I am talking about. Otherwise, if 5 were to be 0, then this parabola you would have spoken about, right? So this is the parabola y is equal to x square, but now this is the parabola y plus 5 is equal to x square. Whenever you add a number to y, the function actually comes down vertically. So this is an incidental learning. Let's not worry about it. Now wherever this function y plus 5 is equal to x square cuts your x-axis, there you get two possible roots. This is your positive root and this is your negative root. Am I right? So let me reiterate. First we started with x equal to root 5, and therefore we could get the function f of x equal to x square minus 5. We graphically interpreted it, we represented it graphically, and you see that wherever it cuts the x-axis, you get your roots, positive root and negative root. Till far, it is absolutely clear what we are doing. Now let's come to the Newton-Raphson method. What exactly it does is, you don't have a graph. All that you have this mathematical expression, and you need to find when exactly this mathematical expression becomes 0. That is, I'm talking about mathematical expression, when exactly it becomes 0. What should be the value of x that I need to substitute so that this becomes 0? That is what Newton-Raphson method gives you. It gives you a value of x when substituted here becomes 0. That is what we are trying to find. In graphing calculator, it is very obvious. The moment you plot this function y plus 5 is equal to x square, you get two coordinates, that is where it cuts your x-axis. Those become root, and you don't have to struggle through Newton-Raphson method. But what exactly happens in Newton-Raphson method? Let us try and understand. So now let's try and draw the parabola over here. So you know that the square root of 5 is around 2.24 approximately, because you can use the basic high school division method to estimate this, or you can just press the button of a scientific calculator and it throws out the value. But I'm just putting some random number, very approximate number here, so that you get a sense of what is going on. You in fact start with an initial guess of 2.1, which is mentioned in the problem, because initial guess, let me tell you, is very important for you. If I were to start with an initial guess of x naught is equal to minus 2.1, I would have started somewhere here, and I would have ended up with this value, the negative root. And since I'm going to incept somewhere here, that is 2.1 positive, I'm going to end up with the positive square root. That is where the initial guess in Newton's-Raphson method is very important. Now what happens? First you start with somewhere over here. This is just exaggerated for you to visualize. Otherwise, these points are located so close to each other that it becomes almost impossible for you to visualize unless it is simply blown out. Because 2.1 and 2.24 are not numerically far apart, but here just for visualization I'm drawing this. Note this carefully. Let me also extend this parabola. You will understand why exactly I'm doing that in a while. First, what happens? You draw a perpendicular. This is the method that we discussed. Please go back to what we did when we were trying to develop a formula for Newton-Raphson method and trying to understand how iterations go on, right? So you start with your initial guess, drop a vertical, and that is you are projecting that point onto the curve whose function you are dealing with, whose root of whose function you are trying to calculate. Wherever it cuts the function, you drop a tangent, because at this instant the curve is being approximated by the tangent. The slope of the curve is nothing but the slope of the tangent, and that tangent is going to hit the x-axis here. That means first what happens, you start with an initial guess of 2.1, and then because of that you actually get a tangent that cuts the x-axis slightly after the point of interest. That means you are overshooting the root by a very small value. And then what happens, you cannot draw a vertical down, you will have to go all the way up. You draw one more vertical again to the function. What did we do? We dropped a vertical and it cut the function at this point. I drew a tangent, and then wherever it cut the x-axis, from there I dropped one more vertical to the parabola, and from there I am going to draw a tangent which almost hits the root. Okay, this is just to give you an idea of what goes on in Newton-Raphson method. First you overshoot a little and then come back to the root. Maybe in one or two iterations you will be able to achieve the square root of the function. Now, till far what we did, we developed a function, we plotted the function, we understood the function, and very importantly we also understood how the shifting happens, because you are meddling with the dependent variable, so the graph gets shifted up or down. If you are meddling with the independent variable, graph shifts either left or right, and this is what is called the shifting property. Whether you are talking about signal processing, whether you are talking about Laplace transform, this property is going to be very, very useful. That's an incidental learning. And also we understood the process, how exactly the Newton-Raphson works, because you started with a guess of plus 2.1. Minus 2.1 would have yielded the negative square root. It's going to yield you positive square root. Drop a vertical, draw a tangent. Wherever it cuts the x-axis, drop one more vertical, draw one more tangent, you get to the root. Okay, so now let's understand this process mathematically, because that is what your university expects. So we have developed a full-fledged XLS. Subsequently, we also promise to demonstrate this method for 1 or 2 examples on calculator, because at the end of the day, across all universities, you are used to using a calculator to carry out this entire process, right? So this Excel sheet you can download. You can see this is the traceability for your Excel sheet, because we have given the code of a certain university curriculum. It can vary from university to university. So we have chosen some random university math code that we have used here to represent the Newton-Raphson XLS. And what does the problem definition say? It says find the square root of 5, and it also tells you the initial guess x naught is equal to 2.1. This is a general XLS you can use for finding root of any function, provided that you change the definitions that we have given here. And here we have mentioned the general formula for the iteration process of Newton-Raphson method. That means n plus 1th estimated root. Okay, that's what is given by this. Suppose if n is going to be 0, then it will give you the first estimated root. Remember, if you put n is equal to 0, this becomes x naught initial guess, x naught initial guess, x naught initial guess. That means you are getting the first estimated root. If you go back and see what is that first estimated root, this is the first estimated root that I am talking about. Because this is the initial guess, drop a vertical, draw a tangent, wherever it cuts, you get your first estimated root. Is that absolutely clear? Now, having understood, here we have calculated both these, that is the function which we derived previously, y is equal to x square minus 5, that's what mentioned here. Because you are going to calculate at every iteration, that is at nth iteration, this is how you calculate. And f dash is nothing but, if you differentiate, you get 2x, because 5 is a constant. At nth iteration, this is the value of f dash. If n is replaced by 0, you get the value of f dash for first initial guess, and also if n is 0, you get the value of f of x for initial guess. That's very important. So these two are done, right? So we have given the formula for this. And also very, very important, even if you are using a Google based calculator, in many of the calculators, because your function can be an awkward one, you are asked to provide the derivative of it. Okay, of course some calculators also are able to calculate. It depends on how you have programmed it. So now coming to the table, what it contains the initial guess, and then this in fact represents the number of iterations. And here we call every time you estimate the root, you call it as estimated root. You can see it is improving. The first one obviously has overshot because you started with 2.1, and you can see this is what I exactly said. You started with 2.1 and you went little beyond the root. You can see your root, actual root is 2.23, but you start with the 2.24, very, very close, and then you come back, and then you see after overshooting, you come back to the root. That's what exactly happening here. So initial guess, number of iterations, x1, x2, x3, x4. That means whenever I say x1, I'm talking about n is equal to 1. That is n is equal to 2, n is equal to 3, n is equal to 4. But here you'll have to be careful. When I put x equal to 0, I get n is equal to 0, I get x1. And here when I put n is equal to 1, I get x2. And when I put n is equal to 2, I get x3. So you will have to be careful. okay, and then the next column is the actual value of the square root of 5 that we have calculated up to 6 decimals, and then this gives the difference between the estimated root and the actual root when this becomes almost 0. Okay, almost 0, practically 0, because it depends on the bookkeeping ability of the XLS. The difference between the actual root and the estimated root, when it becomes almost 0, you halt the iteration and you predict that the square root of 5, that is the fourth estimated root, is the square root of 5. That's what this XLS basically does. That's very, very important, and you can see that you have almost reproduced up to 5 digits the square root of 5. That is, the fourth estimated root gives you the square root of 5. So let us understand this process numerically, and also you can see graphically it is plotted in one Ziffy. You get this particular root. Of course, it is calculated to large number of decimals. It depends on how your program is written, depending on which you can achieve so many number of decimals. So it's an irrational number. You can have a large number of decimals to actual, but we cut it off to get a practical value, that is this. So we have approximated to 6,8. You can see it goes 6,7,9,7,7. Of course, we have approximated it to 6,8. We have cut it off. So that is the root. So what is the procedure? Let's understand. Now the procedure is very, very simple. So the first estimated root, that is x1, if I am talking about, this is my first estimation. Observe this carefully. I think these things are absolutely clear to you. We have explained everything. So the problem definition, the general formula for Newton-Raphson method. Here, if I put n is equal to 0, you get your first iteration, that is x0, f of x0, f dash of x0. x0 is your initial guess, and these are the formula for nth value calculation, that is f of xn. If you replace n by 0, you will get x0 square minus 5, 2 into x0 as f dash of x0. So these values can be calculated. This is my initial guess. Now I am telling you how I have arrived at x1, x2, x3 and x4, and this is actual one, which you can calculate either using a calculator or from the graphical calculator. You can get this and put over here, and here we have just taken the difference of the values. So now let's try and understand how exactly I got my x1. x1 is simple. You first start with x0, your initial guess. So your f of x0, and here you have f dash of x0. How did I get this? In this formula, simply put n is equal to 0. That will give you the first estimated root. So x0 is what? 2.1 minus f of x0 is what? 2.1 whole square minus 5, and in the denominator you have 2 into 2.1, right? So this is what exactly you have here. This is your first estimated root, and observe this carefully mathematically. 2.1 square comes around somewhere 4.41 minus 5, which is a negative number. That means you are subtracting from 2.1 a negative number. That means it actually becomes a positive number. That is where you can see that it has become 2.24 from 2.1, and incidentally you also appreciate that it has slightly overshoot the root that you were expecting. So what you would get? You would get your first approximation as this number. This is what exactly we have calculated. And what about x2? Simply x2 is going to be calculated as follows. You are going to replace your initial guess by this number, that is 2.240476 minus the same thing, that is 2.24 blah blah blah. I'm not worried about it, just I'm trying to explain the process, and divided by 2 into 2.24. So this is what is going to give you your second estimation. And once you get this, again substitute in the process, in the equation, you will get your third estimation. And how do you do that? You simply use your third iteration, that is third iteration value, that is third estimated root. If I call as we have mentioned here, how it is got? It is got by using this x2 in the formula, that is your x is going to be 2.236 blah 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 minus, then you will have 2.236 dash 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 whole square minus 5 divided by 2 into 2.236 whatever, that is I am substituting this, so that will give me my x3, that is the third estimated root. Here itself you can halt because this is almost very close to your root, but we have carried out one more iteration and that will not give you any change which is appreciable. One more method of halting is that if your root is not appreciating, because when you are solving a problem, if you don't have a graphing calculator, you don't have a calculator, you are just blindly doing a problem, then this value will not be available to you. Here we are demonstrating a problem to you, so we have used a graphing calculator, we have used a scientific calculator, we have come out with this value. In a case where you do not know the actual value, how do you halt? The improvement in the estimated roots. You can see here there is absolutely no improvement in the estimated root, but of course from this to this also there is no improvement, except that your fifth decimal has decreased by 1, except your fifth decimal has decreased by 1. So in a practical situation where you are blindly working on a problem where you do not know your actual root, if your root does not improve significantly, you can halt your operations. So this is what exactly is the root. Of course, you can calculate it to any number of decimals if you have the right program or the right calculator. We have cut it off to 6th decimal. So this gives you the fourth estimated root. Here gives you the root very close to the actual value. Now let's recall whatever we did thus far. So we started systematically. We said x equal to root 5 is what I want to find, which led us to x square is equal to 5. That means my function becomes 0, that is x square minus 5 becomes 0. So therefore x square minus 5 when becomes 0 gives me square root. That means this must be my function. So I arrived at the idea of the function, rather the expression for the function. And then we spoke about the graphical representation. So incidentally, we spoke about how if the dependent variable is added or subtracted with a number, how exactly the graph shifts up or down. And if you meddle with the independent variable, it can shift left or right depending on whether you are adding or subtracting the number. You can go back to our video on shifting theorem and Laplace transform and appreciate this concept in its entirety. So now, coming back to the procedure, we very clearly told you that wherever it intercepts the x-axis, this parabola, because you added plus 5, it shifted down, it intersects the x-axis at 2 points. One gives you the positive root, another gives you the negative root, but we are interested in the positive root, so we are starting our journey here as our first initial guess. So once I do the initial guess, you can see I drop a tangent vertical to the function. Wherever it cuts the function, I draw a tangent, approximate that by the tangent, approximate the function at that point by a tangent, that cuts the x-axis. From there, I drop one more vertical to the function and then draw a tangent. You almost get the root. You can also you also appreciated that in 2 iterations you had almost hit the root. So therefore, that is what exactly the process happens. You can see we have actually plotted it, and this is the root of 5. Because this is the parabola which represents the function. When that function goes to 0, you will get x as the root of 5. So now we explained these important things. You started with the initial guess. This is the problem definition. This is the general formula for the n plus 1 estimated root, because when n is equal to 0, you get the first estimated root. When n is equal to 1, you get the second estimated root. When n is equal to 2, you get the third estimated root. And these are the general formula for the value of the function for the nth root, and the value of the function for nth estimated the derivative of the function for the nth estimated root. Okay, that should be understood clearly. And once we understood all this, then we started with the formula. This is the standard Newton's Raphson formula. How do you get? Put n is equal to 0 here. Once you get n is equal to 0, you get your first estimated root. So this is your initial guess, initial guess, initial guess. Whenever I say x naught, that is when you put n is equal to 0 here, x naught becomes your initial guess. And you saw that the initial guess is 2.1. So you are actually getting a number greater than 2.1 because you are subtracting a negative number. You can see 2.1 square minus 5 is a negative number. You are getting a greater number, that is 2.24. And that is where we also graphically told you that you overshoot when you begin, okay, by a very, very small margin. Of course, these are very, very closely located points. And once that is done, then we use whatever we got, that is 2.240476, that is in the same Newton's equation to get our second estimate. So this value is simply replacing our initial guess and we are getting our second estimate. And when this process is continued, because this is going to replace okay, this particular value, that is the second estimate, is going to replace the first x1 value, we get our third estimate. That's what exactly we explained. And in third or fourth estimate itself, we have hit the value of the root very, very close. Of course, the value of the root is approximated to 6 digits, and we have achieved that in 4 iterations. So the fourth estimated root is 2.236068, which is the approximate value of square root of 5 to 6 decimals. So that was a detailed discussion of both the mathematical procedure and what exactly happens when you're doing all this graphically also we appreciate it. So if you have a graphing calculator, this procedure becomes absolutely irrelevant, but you will have to do this from a university perspective. Well, engineering and math are absolutely inseparable. We Innoventions, day in and day out, try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.